Okay, then hello everyone to today's seminar on interval methods in control engineering. And it's my great pleasure to welcome today Sabine Lerch from the Chair of Automatic Control at the Bergische Universität in Wuppertal in Germany. And that's also the university where she graduated in the field of electrical engineering in 2017. And since 2018, Sabine is a PhD candidate at the Chair of Automatic Control Engineering and Control Systems at the same university. And there she's especially working in research on generic LMI algorithms, linear matrix inequality algorithms for the design and optimization of discrete time controllers for multivariable systems. And yeah, that's also the domain where Sabine's presentation will come from today about minimizing oscillation for magnitude and rate saturation for discrete time systems by a DR region pole placement. And we're looking forward to your talk, Sabine.
Thank you very much for the kind introduction, Andreas, and for the opportunity to present my work here. The main aspect of this talk is already published in the proceedings of the ICSC conference last year, and it is a joint work with Robert Dehnert, Michel Rosig, and Bernd Tipken, all from the same chair of the University of Wuppertal. And our main research field corresponding to this talk, as you already mentioned, is an LMI-based iterative controller design method for discrete time systems. And hereby we especially take actuator saturation into account, not only magnitude, but also rate saturation, and with the target of minimizing oscillations of the closed loop. To motivate considering the actuator limits in the controller design, I want to show you this example of a rendezvous maneuver between a space shuttle and a space station. And we designed a controller which takes the actuator magnitude limits into account. And so if there are only magnitude limits, then these trajectories follow. And you can see that the actuator reaches the saturation limit in the beginning, but nevertheless, the rendezvous maneuver is performed stable. But if we have also actuator rate limits now, and we use the same controller, then these trajectories follow. So now the space shuttle is not able to dock onto the space station in a stable manner. And therefore, it is important to consider all the constraints already in the controller design. Now I also want to motivate the optimization task. Often a system shall come back to its operating point as fast as possible. So it is common to maximize the decay rate. This is defined by the maximum value of sigma such that this inequality holds, so that the norm of the states at all time steps k in discrete time are smaller or equal than the norm of the initial states, reduced by an exponential function and some gain m. And this leads to the fact that these two trajectories have exactly the same decay rate, which is 1. And this becomes obvious when we add the exponential function 5 times e to the power of minus k, which is the black line, and to be precise, also minus 5 times e to the power of minus k. And you can see that this orange system is always between of those two lines, so this inequality holds. And the blue line equals e to the power of minus k. So both have the same value of sigma, so the same decay rate. But of course, we would prefer the blue system. But if we maximize only the decay rate, then both could occur. So therefore, instead of maximizing the decay rate, it could be a good idea to maximize the damping of the system. So we need different or additional criteria to find some quality function of the oscillations, and this is addressed in this talk. Now I want to give you an overview about the next about 30 minutes. At first, I will describe the system for which we want to design a controller. This is a linear discrete time system with the only nonlinearity of actuator limits in magnitude and rate. We want to design different controller types, which I will show shortly. And then I will talk about the general stability conditions for magnitude and rate saturated systems. how to maximize the decay rate, and then come to the new optimization task of maximizing the damping. This leads then to an iterative LMI algorithm. Then I will show a few examples and draw a conclusion. So let's just start with the system description. This is a linear discrete time system in state space form, and the representative block diagram. However, in the real application, the actuators would be limited in magnitude and rate. So there are different approaches actually to model this twofold saturation, but it can be shown that this model is the most accurate in the literature, and it consists of a nested saturation function, whereby V is the rate saturation and U is the magnitude saturation, and this is the block diagram. And now we want to have a model of this whole plant. So we combine them in an augmented system. Here we have again the state equations, which we have seen before. So XS are the states of the linear part of the system, and US are the states of the nonlinear actuator. Then we combine them to the new augmented state vector X, which leads then to this augmented system, which is only dependent on the new state vector X and the input U. So we have now this model of the plant, and we want to control it, but we don't want to specify the controller yet, because there are different controller types that are suitable to stabilize different systems. So instead, we want to find a general state space representation of the closed loop for different linear controller types. And therefore, we define the feedback as some gain K multiplied by a new state vector Z. And this consists of the state vectors XS and US, which we have already combined to X. The controller could also have internal states, which I for now call XC. So the size of Z can also vary. And this leads to this general state space representation of the augmented closed loop. And hereby the matrices A, B, K, and F depend on the controller type. And there are actually many different controller types that can be defined by the structure. For example, those in the list here. So we have, of course, full state feedback and static output feedback, and also dynamic feedbacks such as observer-based or dynamic output feedback, PID control, and many more. And to represent them in this difference equation here, we just need these matrices. To get a better overview, I now mark the unknown control parameters in red, and they appear in A and in K. So matrices containing control parameters I marked in orange. And we want to ensure stability for all of those controller types with one LMI method. So as you can see, there can be decision variables in A and K in some structured way, which makes it hard to just apply change of variables. In general, to ensure stability, we can use a quadratic Lyapunov function. Then we will get an ellipsoid as the guaranteed domain of attraction. And then we have to solve this stability condition. For a linear autonomous system, we can then substitute this inside the stability condition and simplify it to this condition. But we have this general representation of the closed loop for different controller types. And unfortunately, this is nonlinear due to this nested saturation function. So this leads to this nonlinear stability condition, which cannot be solved by an LMI solver in this way. But it would be linear when there's no saturation. So one idea could be not to allow the saturation. And this happens when the saturation of U equals Kz and of V K plus Fz. So we can define those linear areas of the closed loop. And this is illustrated in this 2D example. So the linear areas are between those boundaries. So there's no saturation inside this part. So there would the closed loop would be linear, and outside here it would be nonlinear. So we just have to ensure that the guaranteed domain of attraction is inside the linear areas, and then the closed loop is linear. This would lead then to those stability conditions. The first one is the Lyapunov stability condition of the linear closed loop. So now we have here k plus f instead of those nonlinear function. Yeah, the second one is the condition that guarantees that the guaranteed domain of attraction is really inside those lines, those linear areas. But this way, we will never reach the saturation limits. So we have less degree of freedom. Something like bang-bang control would not be possible. And yeah, the input variables would be smaller than necessary always. So the decay would be slower, and obviously the optimization is limited. So it would be better to allow reaching the saturation limits. So let's just assume we have a controller K that can lead to saturation of the actuator. But how can we deal with the nonlinearities then? Therefore, we introduce two auxiliary controllers, H1 and H2, whereby H1 does not lead to a saturation in the magnitude and H2 not in the range. So we can define the linear areas of those controllers K, H1 and H2 here, which is exemplary shown in the figure. So the orange lines are the boundaries of the linear areas of the auxiliary controllers, and the blue lines correspond to the linear areas of the actually used controller K. So if H1 and H2 should not lead to saturation, then the domain of attraction should lie inside of those linear areas of H1 and H2. But for K, we don't want that condition here. Instead, we even want K to be able to saturate. So this would be a possible place for the domain of attraction. You see the different areas here. So for initial states inside the blue area, the controller K does not lead to actuator saturation. But in the orange areas, which should also be inside the domain of attraction, then K could lead or would lead to a saturation. And then this would be the condition to guarantee the place of the ellipsoid. And as you can see, it only depends on H1 and H2. So how can we guarantee stability by that? In the linear case, so when no saturation at all occurs, we would have these feedbacks. This is always valid for H1 and H2, but not for K. But we can build the matrices that consist of all possible combinations of the rows of those linear feedbacks. And these are those matrices theta I. And it can be shown that the nonlinear feedback can always be expressed as a linear combination of those matrices theta I. So in other words, the nested saturation function can be included inside a convex hull of the vertex matrices theta I, but only as long as H1 and H2 do not lead to saturation. So we have to keep that in mind. If we can express the nonlinear function as a convex hull, then this means that we can also express the whole closed loop as a convex hull of vertex matrices. We call them AI tilde, and they are A plus B theta I. And then due to the convexity, it is sufficient to guarantee stability for all of those vertex matrices AI tilde in order to prove stability for the whole nonlinear system, as long as H1 and H2 do not saturate. So this is the second condition here. And now I mark the decision variables in red again, and the matrices containing decision variables in orange. So you see that AI tilde contains decision variables, at least K, H1, and H2, but it can also contain decision variables in A. So the first condition is obviously not an LMI yet. And yeah, with the second we will deal later. So the first one can be reformulated by the show complement, but this is still not an LMI due to this inverse of P. For the example of full stage feedback, then this system equation would follow with the only unknown parameter K. We can substitute that here for the matrices AI tilde. And then we still have this nonlinear inverse of P, but we can solve this by a standard approach, which is, for example, used in or by Bateman and Lin, which uses a change of variables to reformulate this to an LMI condition, which we can solve then. And for another example, for static output feedback, we also only have the unknown parameter K, but with C, which would lead to this change of variables for Bateman and Lin, which does not really work because we have the known matrix C in the middle. So we have to structure Q or K, and then we get conservative results. But there's another approach from Crusius and Trofino, which we can solve, which we can use here, and then we get LMI conditions which are not so conservative. But these two were the two simplest controller types of the list, and this already shows that we have to change the method itself for every kind of controller, and that is not convenient. So we want to find a method which can be applied for every controller type, and so every controller type of the list. So AI tilde should stand on its own here. And therefore, we used a linearization approach. This has already been explained by Robert Dehnert in his talk in January, so I will only talk about it shortly. And the main aspect of it is that this linearization of the inverse of P with a constant matrix P hat is always smaller or equal than the real inverse. So this means if we would solve this LMI, then this inequality is always guaranteed. So we can use it here. We get these LMI conditions. And when P hat equals P, then we would even come back to this original inequality. And if we now, for example, aim at maximizing the decay rate, then we can place the eigenvalues inside a concentric circle and minimize the radius. And this leads then to this optimization problem here, whereby R bar is the upper bound of the spectral radii of AI tilde. We still have then this additional condition that H1 and H2 do not saturate, and this can be reformulated to these LMI conditions. And we can also have, we can define some initial states that should be included in the domain of attraction. So we can build a convex hull around those states and then place them in the ellipsoid by this inequality, which can be reformulated as these LMIs. So now we have a set of LMIs which we could solve, and we could even maximize the decay rate, and this is the basis of the work. Now I come back to the new optimization problem. To minimize the oscillations of the system, we want to increase the damping. And in a continuous time system, the shape of constant damping is such a cone in the left half plane. For example, we could place the eigenvalues in this black cone or in this blue one or this orange one. And if all eigenvalues would be placed on the negative real axis, then this would mean that there is no oscillation. So the damping angle theta should be small. And in discrete time, this cone is transformed to a cardioid shape. So we want to place the eigenvalues inside of such a cardioid. And if we reduce the damping angle, then in the end, the eigenvalues would be placed on the right positive real axis in the stable area, of course, so smaller than 1. And this would mean that we have no oscillations. As an example, I will now consider the damping angle of 70 degrees. Then if we want to place the eigenvalues inside of this area, of course, only the outer lines here are important, but this shape is not convex. You can see it here. So we need to find a convex approximation in order to use this for an LMI approach. And this is the so-called angle ellipse. It's developed by a research team from Slovakia, and it consists of an ellipse, and it's cut off by a cone or by an angle with some intersection point here. You can imagine that this intersection point can be at different locations. So we can have different angle ellipses for one cardioid. For example, 0.9, 0.7, and 0.5. So we have 3 different angle ellipses here, and the question is which one is the best. And if there's much less or more damping, so the angle, cardioid is different, then another intersection point could be wise. So we made an analysis by the difference of the areas of the cardioid and the angle ellipse, and then this trend line follows for the minimum difference of the areas. So we get now an optimal fit for the angle ellipse by using the intersection point from this trend line depending on the damping angle theta. And now we call it theta bar because it's only an upper bound if we place the eigenvalues in the angle ellipse. And for the shown example of 70 degrees, it would mean that the optimal value is here close to the yellow one, so maybe around here. And such an angle ellipse is always convex and can be interpreted as a DR region. The DR region is an area in the complex plane defined by the 3 parameters R11, R12, and R22. For example, a circle is defined by this parameter setting, which can be seen by substituting those parameters in this inequality, then it follows the circle inequality. And for the angle ellipse, follows this parameter setting with the damping angle theta bar, or the upper bound of the damping angle. And this upper bound, if it's set to 90 degrees, means that we have no limitation of the damping, and 0 degrees means that we have the maximum damping. So what we want to do is to find conditions that guarantee that all eigenvalues of the closed loop lie inside such a DR region with this parameter setting and with a small damping angle of theta bar. And this is what I want to do now. So with the quadratic Lyapunov function, this inequality follows, whereby this is the Kronecker product. And I mark again the decision variables in red and the matrices containing decision variables in orange. So this is not an LMI yet, but we can reformulate this by reformulation by Purcell. This is then still not an LMI, but with the reformulations we have seen before for full state feedback and static output feedback, these 2 controller types could be designed. So we could reformulate this condition then to LMI conditions, but we want to design different controller types as well. So we use another change of variables here with a constant matrix p hat. And this leads then to these LMI conditions. And here we can also see that if we set p hat equal to p, then by the Schur complement, this original inequality follows. So p hat is also here an approximation of p. And now let me shortly show you that this new method is an enhancement of the linearization method of Dehner for DR regions now, or for the pole placement in a DR region. With the linearization method, we were able to place eigenvalues inside a concentric circle. So for the new DR region method, we need this parameter setting, and this leads then to this inequality if we substitute those parameters here. And then by a simple congruence transformation, we can restore this LMI, which is exactly the linearization method. So for the maximization of the decay rate, both approaches would be the same, but now we can place eigenvalues in any convex DR region with this new LMI condition. And to point out again the advantage, P is now decoupled from AI tilde. So all the controller types which I've shown in the list, we can design all of those now. And as I already said, the optimum would be that P hat equals P, because then we solve the original inequality. And yeah, the problem, of course, is that we cannot just set P to P hat, because P is a decision variable, so it's not known beforehand. But we can initialize P hat, for example, by the identity matrix, and then start an iteration where we update P hat by P of the last feasible iteration step. Another problem is then that this initialization might lead to infeasibility of the first step. And if that happens, then we don't get a solution for P, so we cannot update P hat, so we don't get any solution. To remedy this, we allow the system to be unstable in the first step by a radius bigger than 1. So we generate more degrees of freedom. And then we iteratively minimize R until R equals 1. So then we have a stable solution. And after that, we can do any further optimization. Now I want to demonstrate this full algorithm to maximize the damping. So it can be parted in 3 stages. As already said, we need to start with an unstable solution because of this initialization. So on the right side, you can see the green area, which is the stable area. So you see that if we also allow the eigenvalues to be outside this area, then the solution is not stable. But this is not a problem, because we will minimize the upper bound of R until R equals 1. And then we end stage 1 and have a stable solution. And therefore, we need this parameter setting of the DR region for the circle. Then in the second stage, we can minimize the radius further. We can even minimize it until it cannot be reduced further. Of course, that would not be necessary to minimize the damping angle, but switching from stage 1 to 3 directly, where we will minimize the damping angle, can sometimes cause numerical problems. So it's easier if the eigenvalues are already inside a circle with a radius smaller than 1. We could stop it at some point. We don't have to go until it cannot be reduced further, but it's performed offline, so we have time. And then in stage 3, we will use the parameter setting of the angle ellipse. And therefore, we start with a damping angle of 90 degrees. So means we have no damping at all. And we end when the upper bound of theta cannot be reduced further. And then we have the maximum damping. To show a few examples. First of all, I want to show the procedure on a numerical example taken from the literature. We designed here an observer-based stage feedback, and the 3 stages are visualized here, 1, 2, and 3. In the first plot, you see the Frobenius norm of the difference of P hat and P. And I already said it should be small, because then we solve the original inequality, or nearly solved it. And it decreases here over the iteration steps. And in the end, in the solution, we have 10 to the power of -7. So it's small enough to say that we nearly solved the original inequality. And in the second and third plots, you see the spectral radius and the damping angle and their upper bounds. In the first stage, we get unstable solutions, but because the radius and the upper bound of the radius is bigger than 1. But after that, we will minimize the radius, and there we don't delimit the damping angle theta. So the upper bound is always 90 degrees. And after that, we don't delimit the radius. So it's 1. It has to be stable, but it doesn't have to be optimized. And after that, then we optimize the damping angle. And the algorithm stops at some point when we cannot reduce this damping angle anymore. In the second example, I want to compare the two optimization tasks on 18 different systems. Hereby, we designed full state feedback controllers, and the systems are numerical examples and real applications. In red, you see when you see the results when we minimize the spectral radius, the upper bound of the spectral radius, and in the blue figure, in the blue bars, you see the results when we minimize the damping angle. And when we minimize the radius, because we don't have any limitation in the damping angle, so it's 90 degrees. And in the blue color, in the blue light color, you see the upper bounds that we minimized this upper bound, and this also leads to a minimization in the dark colors of the real damping angle. And in some examples, you even see that we reached 0 degrees of the damping angle, so we have no oscillation here. To demonstrate those results on some examples, this is an unstable aircraft with 2 inputs, which is the elephant and the canard flap. And we use the algorithm to design an observer-based state feedback. And here the trajectories follow for the outputs, the inputs, and the rates. At first, you can observe that we were able to stabilize this system with both of the approaches, but when minimizing the damping angle, then we get less oscillation, especially here in the inputs. And you can see it also in the damping angle theta, which was reduced from 86 to 70, but without increasing the radius much even. We can also design now a different controller for the same system, which is here, for example, a PID controller. We will see then that the other controller was more suitable for this system because we have more oscillation here, but we can reduce this oscillation by minimizing the damping angle, which you see in the blue color. And as a last example, I show here the unstable VTOL helicopter. And hereby we can massively reduce the damping angle from 70 degrees to 27 degrees. This increases the radius, but this was not delimited, so this is then okay. And in the trajectories, you see that there's less oscillation in the inputs and outputs, and also less overshoot in the inputs. So to summarize my talk, we minimized oscillations by a DR region pole placement, and we could take into account magnitude and rate saturation, and without stability loss, or we could even guarantee stability for those kind of systems. This has been done iteratively, and one of the main contributions of this work is that we can now design different controller types with only one LMI method. And as an outlook, of course, now we can use other DR regions for other control objectives, or combine something like the decay rate and the damping. We can also try to find a more accurate convex approximation of the cardioid instead of this angle ellipse, and of course test it on real applications because those were only simulations here. And in other publications, we have combined the general LMI algorithm with uncertainties and quasi-linear forms. So this could also be an enhancement here. So for now, thank you very much for your attention, and I hope you have interesting questions.
Okay, then many thanks, Sabine, for your very interesting presentation. Definitely we will have some questions. Who wants to start with asking the first ones? Okay, no one has unmuted him or herself so far. Then let me start with the first question. What you did so far is you treated linear system models. And yes, the polytopic uncertainty came into play due to the rate and the actuator separations. Yeah. In order to deal also with nonlinear systems, what you just mentioned at the outlook of your presentation, is one could use some quasi-linear state space representations, and one could overbound the nonlinearity again by a polytopic uncertainty model. Now, what kind of difficulty do you see with doing so? Would it be straightforward, or do you see some kind of, let's say, unsolved methodological aspect that needs to be treated?
I think it depends on where the uncertainties appear. Maybe we can go back some slides to the where we see the structure in A or in AI tilde, because if the uncertainties appear in A, I don't see a lot of problems here. Let me just go back. These were a few slides. Sorry for that. Okay, this is what I wanted to see. Okay, so if we have like full state feedback and then uncertainties in A, then this should not lead to problem, because we don't have then any linear or any nonlinear combination of some convex approximations. Of course, only if the uncertainties are linear. But if we would have, for example, uncertainties in B, then this would lead to a problem here, because B and K, then in a bilinear combination, and then we would have to deal with that. Yeah.
Okay, what you also mentioned is this approach of Crucius. How you formulate it is the way that if you have point-valued matrices at the system output, that means your system output matrix C is perfectly known, then you directly have a linear constraint, linear matrix equality constraint in this case, and the stability is then ensured by a matrix inequality. There exists also a dual formulation that is quite well suited for the case that B is perfectly known and C may be uncertain.
Okay.
What about the case that both of the matrices are uncertain? That you have maybe some uncertain sensor gain on the one, certain actuator gain, uncertainty in C and in B. Do you have any idea about that? What would happen in such cases?
I would say that this is a problem, and I actually don't know how to solve that. Maybe there are some approaches then.
Yeah.
Yeah, I don't know.
Yes, I assumed this exactly the same, because then I think it's really only possible to just find a much more conservative solution than at the end. And yeah, unfortunately, I think this is also a point of, maybe fortunately, a point for future research.
Yeah, maybe.
Yeah, and then since I already see the slide here, I appreciate very much also in your PhD thesis, the unified treatment of the totally different structures of controllers. On the one hand, full state feedback, static, dynamic output feedback, observer-based feedback, whatever. What about cascaded control structures? Do they also fit into this setting?
I haven't considered them yet, so I cannot say it out of my mind. I will try that, but I cannot do it in my mind right now. It could be that there's some problem with some bilinearities, but it could work. I'm not sure right now.
Okay, do we have further questions from the audience? Because I still have several. Okay, you want to deal with a nonlinear system, for example, stabilizing an inverted pendulum. And the typical control strategy would be for an inverted pendulum, first of all, to perform a swing up, maybe energy-based swing up, and then in the vicinity of the unstable equilibrium of the upright position, you switch to a linear control strategy. Yeah, and I think definitely what is doable with your approach is to perform rate and also magnitude restrictions of the linear controller can be taken into account in the vicinity of the upright position.
Mm-hmm.
Do you have an idea how to, let's say, switch between both types of controllers in a smooth manner? Could this be integrated?
You mean like something like gain scheduled control?
Yes, it could. Yes, I'm thinking into this direction, whether this would be some kind of gain scheduling, that you're fading up controller and fade in your approach.
Yeah, the question in this part would be where to switch, because I think for the controller that brings the pendulum upwards, this one can only stop when it's really upwards in the end. Yeah, I don't know if I think the switching would be very late, would be after the first part is done. And then something like fading out of this first controller would maybe even be better to directly switch, but I'm not sure about that.
Yes, I think the question would be, since you have shown this ellipse, or also the ellipse from which you have cut off some areas to avoid saturations, I think the prerequisite then would be to prove that you definitely stay within this ellipse after switching.
Yeah, good point. Yes,
because then you would reactivate again, yes, let's say the swing up controller. And I think this would be a nice idea, for example, in the design phase, to combine, on the one hand, your optimization for the, let it be observer-based feedback or directly as a full state feedback, with a simulation-based approach that uses a verified integration technique that proves that you definitely stay within the ellipsoid and never leave it again.
Yeah, only if we model it well enough, but yes.
yes, this is what I also assumed, definitely.
Yeah, good idea. We will try that. Yeah, thank you.
Okay, further questions from the audience? Okay, let me check. Do you have a final one? Yeah, I have a final one. You mentioned also in the Outlook is a combination with the work that also Robert presented a few weeks ago. With this desensitization with respect to noise. If you have noise, let's say noise-induced oscillations, is it then still possible to prove that you stay in the domain like you did? Or would it be something like, let's say, with a certain amount or a certain degree of confidence, you will stay in this domain? I'm not sure how the formulation then will look like.
Yeah, I think if it's disturbance or something like noise in the sensors, then we would have to enhance the model with some noises, and then use this iterator approach in combination. Then this would not be enough here.
Yes, but I assume your results then would be you have proven something like stability with a confidence of, let's say, 80%.
Yeah. Yeah, that wouldn't be very good. Then,
yes, I think it makes sense to think about this.
Yeah.
How the formulation would then exactly look like.
Yeah.
But definitely it is practical because so far, yes, I was also co-author of the other work. Definitely, yes, at the moment we assume that you could have arbitrary large magnitudes of the control.
Yeah, and but we can combine it. Yeah.
Yes, and how to combine this in a reasonable manner? Or how the interpretation of stability then would be.
You mean if we combine the two approaches here?
Yeah, yes. Because also the original formulation is stability in the average.
Yes, but if we enhance it with the disturbance, then I don't see the problem, actually.
Okay, let's rediscuss this offline.
Okay, yeah.
Okay, do we have other questions? Okay, I assume it has been perfectly clear. Then again, many thanks, Sabine, for your interesting presentation. And yes, we'll meet each other soon again. This time, Friday in 3 weeks, on the 24th of March, we will have our next presentation. And until then, I wish you a nice Friday afternoon, weekend, and see you soon.